Thank you very much. First, I want to thank the organizers for inviting me to this program and to have this opportunity to sketch out to you the current situation in terms of our understanding of how the first black holes formed in the universe. So Marta has laid out the sequence of the kinds of topics that we want to look at, and I'm going to focus very much on the formation of the first black hole. So let me first point out at the outset that one of the key issues has been the physics of the gaps. And this is the gaps in our understanding, both in terms of simulations of physical processes that can explain how you assemble the first black holes, that is going from cosmological scales, so kiloparsecs, megaparsec scales, all the way down to parsec scale. So that flow, that gas flow, we know that black holes exist and we know that they grow copiously, but exactly how the gas actually gets funneled from the largest scales to the smallest scales is still largely poorly understood. So we have some mechanisms which we know would work, that could work, ought to work. And we have some heuristic models. So what I want to sketch to you today is how our understanding has evolved in starting with some simple heuristic models, then attempts at simulation, and obviously the connection to observations and how you can actually test various possibilities using data. So to give you a brief outline, just want to sketch roughly what we know for certain about the growth of black holes. There's a lot of uncertainty, and I will try my best to point out to you where the uncertainties are, what the key uncertainties are, and therefore what the open questions are. So there's a lot of observational evidence now at low and high redshift for black holes. And then I'll move right into the seeding models and basically the contrasting the sort of two schools of thought of light versus massive seeds. And I'll sketch out what those two models are, what the limitations of each of those models are, what the predictions are, and then move on to the open question. So before I move on, I first want to say thanks to many of my collaborators. Over the years, I've worked with a lot of people who are actually in this room. So I just want to say a special thanks. It's been wonderful fun working on this really messy, complicated problem. So this, I'm actually stealing a graphic that David Ballantyne made very nicely for a recent grant proposal that we put in. And so this is, these are sort of the challenging problems. So they are not detached in the sense to make the first seeds. In order to have a complete understanding, you also need to understand fueling. But what I'm really going to focus on, try my best, is to give you a good view of what's going on with our understanding of formation. And as I said, again, it's the coupling of scales that makes this a very, very challenging problem. And all the work that I'm going to be talking about is going to be in the context of the standard structure formation theory. So this under this sort of rubric of the CDM paradigm. So the CDM paradigm tells you that we're in a dark matter-dominated universe with the dark matter being in the driving seat, and there's copious merger. So we know the question, however, is what is the relationship of mergers and merger activity and funneling of gas during mergers to the formation of the first black holes, as well as the growth of black holes subsequently. Okay, so the first thing we do see about black holes, and this has to guide the modeling that we do, is the fact that most black holes that we see in the universe are accreting very radiatively inefficiently. So very, very piddly accretion rates. So for example, the galactic center is a good example of that, right? So this sort of is the hard reality. So we need to understand how you can grow the hole. To grow the hole, you need pretty high accretion rates. But what we end up seeing ubiquitously in the local universe are things that are basically shut off or are accreting at very piddly rates. So we just need to keep that in mind. And what we really like as theorists is thin disk accretion. It's a beautifully posed problem. We understand how to do it. It's radiatively efficient. And this is most likely the sort of the growing feeding mode for black holes. However, this is very rare in the local universe, okay? But this is ubiquitous in the high redshift universe, luckily for us, because we think that most active quasars, of which we see many, are actually powered by accretion. So the other thing in terms of observational landscape that we need to keep in mind are that we have some globally average constraints, say, for example, from the X-ray background, which is produced due to the population of accreting black holes, some of which are obscured, some of which are not obscured, over cosmic time. And then, of course, we have moved now from finding a curious, odd very, very high redshift accreting black hole, which is a quasar, to deriving populations of them. So the thing with CDM, the key thing with CDM is that you find one freaky object. So you find one ultramassive black hole, even at redshift 6, 7, 8, what have you. One or two we can accommodate. That's the nature of CDM, right? Because there's a small sort of high sigma tail in terms of fluctuations. It's a small tail, but you can accommodate a few objects. Everything becomes interesting and complicated when you start finding populations of these objects. You start finding a population, even if you see only the bright tip at redshift 8 or 7 or 6. And it turns out that these extremely high redshift observations, not of individual objects, but hints of a population, are really the constraints that we have for the early formation models, okay? Because a lot of other dynamical activity in CDM happens from the formation stage to the stage at redshift 0 when we actually have detections, we have measurements of their masses, et cetera, et cetera. And I just want to point out that, the luminosity functions of quasars multi-wavelength are used as constraints for the modeling in the growth history, okay? And I just want to bring your attention back to the fact that, what does the local M sigma relation tell you? So this is the correlation between the velocity dispersion of the bulge and the central object, the black hole. And so I like this version of this, which is Cahan's version of the M sigma, in which you see the error bar. So once again, the uncertainties are quite large. There is a correlation regardless. And the point is, I think the work that Marta and several others have done in sort of developing these histories, accretion histories, shows that there's a lot of interesting physics that's coded in the low mass end of the black hole mass function, as well as the high mass end of the local black hole mass function. And it turns out, the reason I'm even showing you this, it turns out that the formation models have consequences for these two ends. Despite the fact there's a lot of complex star formation, dynamical activity that happens in the universe to bring galaxies down locally to this correlation. So the thing to note here is, so the two things to note. First is that we are seeing quasars out to very, very high redshifts, which are powered by supermassive black holes with mass estimates of the order of 10 to the 9 solar masses in place by redshift 7, 7.5. Okay, so that's that. Then we actually, it turns out, and they're very, very common. So you need to make roughly one black hole per galaxy, and that's what the local observations are suggesting. So, so these are sort of, if you will, the boundaries of what we have observationally. So any phenomenological model has to obviously accommodate these two boundaries, right? So then, one can get a little more sophisticated, a little more into the details. So that was just abundances and numbers, and you get a little more into the details. Now we have a pretty nice inventory of the black hole, estimates of the black hole mass function. This is work from Brandon, who's here, of the most massive black holes in the epochs from redshift 1 to 4.5, and that's a bulk of the age of the universe. That's also the time in the universe when bulk of stars are forming. So the other thing that we do know is globally averaged, not in every individual galaxy, as we now see from various work from various surveys like Candles, and I think Ezekiel will be talking a little about that later today, is that globally averaged, the star formation rate actually tracks the accretion history onto black holes. However, that may not be the case for individual sources, right? So every galaxy that hosts a black hole may not actually be forming stars copiously, or the most massive black holes may not be sitting in the most luminous galaxies. And we'll hear most of those complications as we go along. So, but this is roughly the landscape of observational data that constrains our modeling. So let me just launch into this old view graph, which I totted up by Martin Rees, who came up with the various channels for the formation of black holes descriptively. And what I'm going to really focus on, I'll talk very briefly about making the first black holes from the remnants of population 3 objects. I think Jared and John Weiss will be talking about that later today. And I'm going to focus much more on what's called the direct collapse channel. So where you have a gas cloud and that collapses without fragmentation. So the key there is that you have a gas cloud that reaches very, very high densities, concentrating gas in the nucleus of a protogalaxy without fragmentation, suppressing star formation. and preferably in pristine environments. This is much more easy to do in pristine environments, so at very, very high redshifts with very low metallicity. And of course, there's work recently that shows that perhaps you could continue this process. Maybe you can dispel the fact that you need pristine material, unenriched material. And we'll hear about that later today, probably from Sylvia. But for now, let me focus on the sort of the early heuristic models, which are essentially looking at these two main channels. So you have population 3, so the light seeds are basically population 3 remnants. Basically, you form the first stars, they evolve, they collapse, and the first star originally was believed to be quite massive, it could go up to 1,000. That's been revised down, as I'll show you in a minute. And you could end up with a remnant that's between 10 to 100 solar masses. And then these seeds are plunked in very high gas-rich environments. And you may actually need brief periods of super Eddington accretion to actually grow the black holes that power redshift 6 quasars. So the other option, but we're running into trouble with that because of the kind of steady high rates of accretion that you would need to produce what we now see as a population of bright quasars at redshift 6 and possibly at 7. So then the idea was, can we ease the constraints on accretion by coming up with a simple fix, which is try to see if there are ways to make more massive black holes ab initio, right? And so this is not new. This is work that's been done for a long time theoretically. And here are the basic ideas that you have this massive gas cloud, which accumulates in the nucleus, as I just mentioned. You form something like a supermassive star maybe at the late stages, and it's often been referred to as a quasi-star, but it never fully relaxes, and it keeps growing till you have collapse, and then you can start making black holes that are about 10 to the 4 solar masses. So let me quickly give you a little more detail in terms of what the challenges are, current challenges for the light seed models and the massive seed models. So the first challenge for the population 3 remnant light seed models is that originally it was thought that the first stars themselves were a lot more massive. Now with refinements in the code and improvement in resolution, we actually see that you don't actually form a first star, you form a cluster of stars, and the mass of those individual stars is actually a lot lower than we thought. So the remnants subsequently also become lower mass. So the other challenging problem is that in simulations, state-of-the-art simulations, you find that the black holes are simply not growing very much down to even redshift of 8, right? So remember, we need to start making a few monsters, a few 10 to the 9 solar masses by redshift 6. And they're simply not growing in the simulations, in the current simulations. And even after sort of POP3 formation has ceased, and you may say, well, maybe it's a radiative feedback from existing POP3 stars that's preventing gas from flowing into the center and growing these holes. It turns out even when POP3 formation has ceased in halos, you actually don't see a whole lot of accretion. In fact, it also turns out, because now you no longer form an individual black hole, but you form a cluster of them, that the dynamics and the kicking out of those black holes becomes relevant. And it turns out that most of the black holes spend much of their time in the wrong places and not very gas-rich places, not conducive to growing dramatically. And so that has been the most recent motivation for looking again at massive seeds. And the details of this work, I think John Wise and Jarrett will be talking a lot more about the specific simulations and what the current advances are in terms of modeling this cluster of black holes and their growth. So the massive seeds are basically ideas that have been around. They've been theoretical ideas. In fact, they've been heuristic ideas for a very, very long time. And only now we are at a stage where we can start doing some simple rudimentary simulations to see if these work. So the basic idea, which is kind of neat, is that obviously what you need is you need some mechanism for viscous transport in early pre-galactic disks. We know in the CDM-like models, when baryons fall into collapsed dark matter halos, that you automatically get a nice sort of disky configuration. The question is, how do you transport angular momentum quite efficiently out, and how do you move the mass in to a very dense, to the dense part of the nucleus? So the theoretical models that sort of date back from the mid-90s have talked about how you could just have some kind of non-axisymmetric instabilities, that like bars within bars kind of stuff, that would funnel matter down and start giving you these very, very massive gas concentrations, which will most likely form these very massive seeds. And these seed models can give you seeds between 1,000 to about 10 to the 6 solar masses. And the question is, what happens after that, right? So you have this gas blob in the center, and then there was a lot of theoretical work, and now, as I said, slowly some computational work. So the stage after assembling that gas blob there, most likely that gas blob goes through sort of a supermassive star or a quasi-star. And so the direct collapse, these direct collapse models, the early models focused on having pristine gas. And that was easy because you had only atomic hydrogen as your coolant, and you even suppressed molecular hydrogen cooling. And that's because you have the Lyman-Werner radiation. So that's sort of been the new thing where we've understood how this could actually work physically. And so it turns out that these models can theoretically produce about 10 to the 5 solar mass black holes. They are rarer. They are produced in fewer halos than where you would get the light seeds. And they hinge upon the fact that we have these mechanisms for angular momentum loss that are quite effective, right? And so the first sort of sets of actual simulations of this process of following the baryonic collapse in these pristine halos, which have only atomic cooling. So this is a graphic from a paper by Reagan and Hainault in 4 to 5 years ago. So let me just give you a very quick glimpse of how this works. So you have this dark matter halo, you have a pre-galactic disk, and you form a little central massive object in the center. And so now we've all been able to start doing some of these toy simulations. Again, the problem has been doing fully consistent, large-scale cosmological flows all the way down to small-scale AMR stuff, right? So this is an ENSO simulation with a former student of mine, Andrew Davis, and Sadek Kochfar's group. What we're looking at here is focusing in with 16 to 32 levels of refinement to see again, the question is, what range in density and temperature can you go? How much further down can you go compared to sort of the first? So these are halos where you bypass the formation of the first star, right? So in a way, you're looking, so they are the low angular momentum tail. And so there's been recent progress in this, both from our group as well as a paper out from Choi et al., Choi, Schlossman, and Begelman, where they are looking at they are trying to focus on the supermassive star, the sort of quasi-star phase, where you have this very extended envelope. And to quickly outline what is nice about this model, I'm going to move away from this very quickly, is that because it's in the context of CDM, you actually naturally get a relationship between the mass of the final black hole and the properties of the halo. So for example, some measure of the angular momentum of the halo, like the spin parameter or the mass of the halo, and so on and so forth. So this is very interesting because in the population 3, the light seed models, you don't have any such correlations, except from the fact that every 3.5 sigma peak or so in the dark matter distribution can seed one of those halos, which is a 3.5 sigma fluctuation, could potentially seed and form the first star, and therefore the light seed. So the quakes, let me quickly point out that because there's been recent progress on this. So this is the final stage after you've accumulated gas in the center, as all these heuristic models suggested. The question is, what do you actually have? You have this big envelope, and you have the central massive object in there that can then rapidly grow and accumulate mass and reach about 10 to the 5 to 10 to the 6 solar masses. So this is something that is currently being worked out. So how do we figure out the consequences of these models? So this is the mass function, the initial mass function of seed black holes at, say, redshift 20 or something. And what you see in the blue histogram are these massive seeding models. So there's a real range. And what you see here in the red panel are population 3, the light seed. So notice that this is the initial seeding, and then you do the standard procedure of following it through with mergers, and you can make a set of standard assumptions that every time you have a merger, you have a growth episode, so you have a merger-triggered accretion episode, and so on. And we can then compute what the predictions are for at redshift 0 for the M-sigma relation, for instance. So what's shown here is the data with the error bars here in black, and what is shown here with the colored dots are from several realizations of these Monte Carlo realizations of these models for various efficiencies of initial black hole formation. And notice what you find, one of the key predictions is the halo occupation fraction, that in the models with massive seeds, there's actually a fraction of galaxies that do not host a supermassive black hole at low redshift. And that's one of the key differences. And of course, the other differences are, if you look at the journey to the M sigma, how do you actually set up this correlation? The journey is very different. For massive seeds, you are actually overmassive compared to the local M sigma, and so you actually move by assembling the stellar components, typically. So much of the growth occurs by moving towards assembling the stellar component, whereas in the light seed models, you are undermassive compared to the local M sigma, so you actually have to have periods of very rapid black hole growth to actually put you on the local M sigma. So we can calculate, because the complications, of course, are we have to make assumptions of what happens during mergers, how much gas is delivered to the center, how much gas is actually accreted during every episode, and whether there's some steady accretion along with the merger-triggered episodes over cosmic time for both these models. So then there are lots of messy assumptions, a lot of unknown things, but the point is we are applying the same physical processes to the two different seeding models, right? So we're not changing anything else in terms of our assumptions, except that we are starting with two different sets of seeds. So one of the interesting consequences that is found, so now we're trying to see what are the observational consequences, right? So one of the interesting consequences, inevitable consequences, is that the massive seeding models suggest, because of the journey to M sigma being fundamentally different, that there will be some galaxies, high redshift galaxies, which will have obese black holes, which will have black holes that are much more massive than the stellar component would suggest for those holes. And it's very promising because these will be the pristine, if we consider the pristine halos forming the more massive seeds, then there are particular signatures that potentially JWST could see. So, there are a whole host of predictions from evolving these massive black hole seeds, and we actually will be able to discriminate with particular sets of data. So I want to close with what I think are the two key sets of data that will help us discriminate these models. So first is this low mass end of the mass function. As I said, the black hole occupation fraction at low redshifts at the low mass end is different for these models. And the massive seed models suggest that the occupation fraction is actually there are going to be galaxies which do not harbor black holes, or that the black holes will have a lot of scatter around the M sigma relation at the low mass end. Of course, that's a challenging end to make measurements, but preliminary support, I would say, and evidence for this is from work from Jenny Green and Louis Ho. Their sort of inventory of trying to find the masses, go after masses for the low mass end of the mass function, are sort of supportive. So you see a lot more scatter. But much more data needs to be garnered there to really see if there are any systematics that are actually biasing our estimates there. But that's a work, as you know, that's an area of very active research. So in my opinion, there are sort of two other very interesting signatures. One is, of course, the faint end of the X-ray luminosity function of AGN/quasars. I'm going to use that interchangeably. And the merger rates for the massive black hole binaries over redshift. So this would be the gravitational wave signal that's predicted. Now that will be different too for these two models. And I think, so these are looking to the future. Obviously, there are no particular satellites or instruments that are very close to our horizon for either of these. But, we are pushing down with the luminosity function of AGN with deeper and deeper Chandra observations, for example. So, I think the prospects are we'll be able to start saying something about discriminating these models. So I want to close with a couple of slides. But I think what is very interesting, though, is that no matter what seeds you start out with, there are some very interesting insights that we can have, that the average Eddington rate that is needed to grow, say, a light seed is such that you need a very continuous accretion rate of about 0.4 times. Sort of average accretion rate has to be extremely high for light seeds. So if we want to stick with light seeds, or we think that light seeds are viable, then we need to be sure that the physical conditions, the gas, the environment is such that such rates can be sustained. So obviously, massive seeds alleviates that problem. For massive seeds, it's much less stringent. But again, the one thing we need to remember is that individual sources, so finding an individual galaxy, a quasar at redshift 7.5 or 8, which has a 10 to the 10 solar mass black hole, is not a challenge to the model. It's actually describing the populations. So now I want to talk briefly about some new ideas that I think are extremely interesting. And this is an idea that I think Lucio and his collaborators will hopefully talk about, which is making massive seeds. So basically, during mergers, late-time mergers of gas-rich galaxies, gas is pumped to the center, funneled to the center. And here, again, you have that you're doing away with the need for unenriched gas. So you can have enriched gas, and you can just still pack it to the center and start making some massive seeds. So I want to close with what I think are some interesting open issues and some challenges for models. So it turns out that there's a set of conditions, no matter what the seeds are, there are a set of conditions that are required to assemble the most massive black holes at all epochs, not just the first ones, but at all epochs. And that's really been a challenge. And it turns out that having initial black hole seeds being very massive alleviates that problem, allows you to actually match the data, because now we have the data from Kelly et al. And that, you need to have brief periods, models need to allow, they require brief periods of super Eddington accretion very early on, and you probably have periods of obscured growth. So these are features that every model actually requires to have as an ingredient. Okay, we have a lot of play, but these are things that you cannot get around. So one thing that's very interesting that I want to close with is the fact that in our strong desire to solve the problem of quenching star formation at late times, people have used AG and feedback a little too effectively. So what that does, it's prematurely stunting the growth of black holes, and our inability, and therefore an inability to produce the massive end of the black hole mass function at low redshifts. And it appears that a long-lived steady accretion mode is a must, that is needed throughout cosmic time. So I'll just stop there. So these are sort of what have emerged as challenges to seed formation models, no matter what, whether you start with light seeds or with massive seeds. And the issue with massive seeds is that it alleviates, the requirements are less stringent with massive seeds compared to light seeds. So I should just stop here.
Thank you very much, Priya. And now we have some discussion about this. Take your time. We have 15 minutes, so you can ask all the questions that you want. And let's start. Julian.
Could you elaborate a bit?
Mm-hmm.
Do I really need the mic?
Yes.
Or is this
Yes.
recording?
Julian, maybe not.
Julian, you need the mic.
Okay. Thank you. Could you elaborate a bit on the switch that determines that certain galaxies will go all the way to pentaphoric 5 solar mass accumulations in the center without fragmentation, whereas others produce clusters of tens of solar mass stars instead, and suppresses examples of masses in between?
Right, so I don't have a full explanation for how you get that, entire dichotomy. But what we do know, and what we have a rudimentary understanding of, is that the angular momentum of the gas in the pre-galactic disk is likely the key ingredient here. But what is becoming really clear, though, it's not the large-scale properties of the angular momentum, but the actual angular momentum during the collapse process. And I think what is puzzling to all of us right now who are doing simulations or managing to do simulations on some scale or the other is that, initially I definitely was quite wedded to the description where, you have this spin parameter for the halo, and in CDM, the spin parameter of the gas follows that of the halo initially, and that's actually the proxy for everything that happens. It turns out that the angular momentum distribution in the outer reaches of even a protogalactic, pre-galactic disk have very little to do with the angular momentum exchange and content of the inner part where all this baryonic collapse is actually happening. So I think all I can say at the moment is that originally we had a very simple picture that the large-scale angular momentum was sort of a proxy for picking sites which had low angular momentum. So what you did was you looked at dark matter halos. They follow a log normal distribution in the spin parameter, which is basically a measure of the rotational support. So that was something like this, and we said, okay, the very, very low angular momentum, this is P of lambda versus lambda. So the really low lambda dark matter halos are going to be preferentially the places that host where you'll form these massive disks that most likely form the massive seed. So that would be sort of this end. Now, but it turns out that this actual large-scale description of angular momentum support might not be a really good proxy for what's happening in the nucleus. So I think, Lucio, if you're going to talk, you can probably talk a little bit more, and maybe John Wise will be talking a little bit. It's probably turbulence. Not that I need to tell you about this, but it's probably something that has to do with which pre-galactic, proto-galactic disks can go bar unstable or can have some non-axisymmetric instability set up in them more effectively that can prevent fragmentation and funnel mass in. So all the work so far has really hinged in the context of CDM in terms of the overall low angular momentum tail of the dark matter host halo. But that looks to be slightly problematic because the inner gas processes in the inner part of the nucleus are quite decoupled from the large-scale properties. So I would say that's sort of where we are at the moment. But the earlier models, especially the work with Giuseppe that I did, we were very gung-ho about using lambda as a proxy. But it looks like that's problematic right now.
Priya, how do you base the statement on the star formation rate being too suppressed with AGN feedback?
Right. So the fact that the current assumed efficiency for feedback from AGN, we think is it's too efficient. The models assume very high efficiency because as I said, what it really does, it suppresses. It stunts prematurely the actual growth of massive black holes. And we find that by trying to compare models to the data from the SDSS broadline quasars, where we now have a pretty good understanding of the mass function of the most massive black holes from redshift 1 to redshift 4.5. So that statement comes from the difficulty in matching models, these accretion history models, to that data set. And that data set is actually quite robust. I mean, there are issues of completeness at lower masses, but the high mass end of the black hole mass function, and Brandon can correct me if I'm too optimistic about this, I think that's pretty robust, wouldn't you say, Brandon? The massive end?
As far as incompleteness goes.
Yeah. So, I mean, I think this statement comes from that. So what we find, we have enormous difficulty fitting the high mass end of the black hole mass function at most epochs. So
what are the models here?
So these are just the merger-driven Monte Carlo models. So these models,
Okay.
Where you start from the seeds and then you evolve using the standard machinery. Those models. Yeah. But you see, the reason this is interesting is, initially we thought that finding a few black holes at redshift 6, right, really massive ones, will solve the problem if we do super Eddington and if we can produce them. But it turns out that the massive end is a problem at every redshift. Okay, so down to redshift 1, making the most massive black holes is still a challenge for these models. And part of that can be alleviated if the efficiency of AGN feedback is tuned down. And the reason, that was assumed to be as efficient as it needed to be was because we were trying to solve this other problem with star formation, which, is a different scale problem. It was a cute solution, but, I don't think we have a good enough understanding yet.
With regard to your last point there, with the problem of gravitational radiation recoil and black hole mergers has been interesting to many people. And the question has arisen whether if there's accretion is necessary to solve the final parsec problem. Does that automatically align the spins of the two black holes, which is unfavorable for high recoil velocities? So I think you raised the question of whether or not it's even required for to solve the final parsec problem. If this steady accretion is going to occur, then is that unfavorable for kicks?
Right. I think that the point with the long-lived steady accretion is that there have to be very natural solutions to the last parsec problem, basically, and that it should be such that it doesn't get disrupted easily by any other dynamics that's happening on larger scales, be it recoils, be it other collisions. And so the one thing that I can say is that, for instance, when we look at, once again, the fact that you need a steady accretion mode, this arises from trying to make the most massive black holes locally and in a range of environments. So in a recent paper that we put out, we actually looked at the difference between sort of the same sort of assumptions about the accretion history, but slightly different environments where the dynamics are completely different. So in a cluster environment versus a void where there are very few galaxies versus an isolated galaxy. So a lot of there have been some very nice simulations where people have tried to integrate various environments. But I think what I'm trying to say here has to do with the fact that indeed the last parsec problem has to have a very natural solution, a robust solution that doesn't get disrupted too easily. So something about the geometry on the smallest parsec, sub-parsec scales, there has to be a robust physical process that doesn't get easily disrupted by whatever else is happening on even 100 parsec or a kiloparsec scale.
Back in 2008, I and Jian Hu showed that the scatter in the M sigma diagram is indeed greater at the low mass end, and it was due to galaxies which possessed bars, and they may indeed be pseudo-bulges.
Yeah.
So that picture still continues today. When you remove galaxies which have bars, the scatter in the M sigma diagram's tight, 0.4 dec.
Yeah.
Now I'm wondering, with your work, the larger scatter that you find at the low mass end, is that at all associated with bars? And if not, there's a problem.
Right. So as I said, when it comes down to the particular geometry of the nucleus, our models are heuristic. Right. So you're actually the reason why you have a low occupation fraction at the low mass end and you have more scatter on the low mass end has to do with the fact that there will be some low mass halos, recently formed low mass halos, that may not be seeded or may have been seeded without, which have a quiet merging history. So that's in the context of all these models where mergers are the pistons where you deliver gas to the center. So that's the sort of basic model, right? And how the gas actually makes it to the center, whether you form a bar within a bar in every individual realization, is not something that we actually model. But yeah, I am aware of your work, and I think that our description of why the scatter is large has to do much more with the merging history of because that's the picture. The picture is a merger-focused picture where we don't actually look. We don't have a model. I mean, there are people who do this work who have those models. I mean, for example, Rachel Somerville and her collaborators have these semi-analytic models. And I guess to some extent, Sylvia has these models where, the formation of the bulge and the disk, etc., are part of this picture. So in our models, they are not part of a picture, so I can't actually say that, if I remove the candidates in our realizations that don't actually have bars, we don't actually follow in that kind of detail. But yeah, I mean, I do know your work, and that holds, absolutely, yeah. I didn't really talk today about the sources for the scatter, and when the scatter is tighter, and what the implications are. There's been a lot of back and forthing looking at the scatter depending on morphology. With Cormandy and Bender had this interesting paper where they argued that the morphology dependence on the tightness of the scatter is telling us that the dark matter halo is really not implicated in black hole formation. We think that that's simplistic. We do agree that the dynamics of the gas in the nucleus is quite decoupled, as I said, from the large-scale properties, but the dark matter does have an important role to play at pretty high redshift because it really does drive the formation of structure overall.
Thanks. Regarding 2 questions ago, actually accretion aligning black holes, so partially aligning black holes, enhances recoil, does not suppress it. That's what the latest full numerical simulation show.
The question was, what is the role of, what does accretion do to recoil?
Okay. Are you looking to me for an answer here? What?
No, I'm looking for your question. I think that was done. He was adding there was a numerical simulation.
Good. So I was going to come back to this point about the inefficient feedback.
Yep.
And we know that in massive halos, radio galaxies, for example, and massive clusters, is where we see the most direct evidence for AGN feedback on really large scales. Do you feel? Because I'm getting the impression that this is a theoretical result. That in simulations.
No. This is, as I said, this is the inability of most models. And when I say model, these sort of accretion histories, Monte Carlo merger trees,
sure,
with some assumptions of how much gas is delivered upon every measure, blah, blah, blah. In those kinds of models, if we try to fit the data for the mass functions of black holes derived from the broadline quasars in Sloan from redshift 1 to 4.5, all the models, no matter what assumption you make about whether the gas that is delivered to the center scales as circular velocity to the 3, 4, 5, what have you, have enormous difficulty in reproducing. So that's where this statement comes from. So it comes from trying to match the observations with these sort of heuristic models. I'm not saying this from doing a large n-body simulation.
Sure. Sorry, I didn't express myself very well. I guess my point was just that there's a lot that we don't know about accretion and feedback, and that we're assuming in all of these models, myself included. And so I'm just wondering whether there's tension between what we're finding in these models and the observations of AGN feedback.
Right. So as I said, right. So even though we play, I think Marta and I even ran a simple model where I think we double the mass at every merger. So you do we know very little about what really is going on with the details of the feedback. Right? We know very little, and I think everyone would agree on that. We have some models, we have some scaling relations. So we played with a whole bunch of scaling relations, and we still find that this portion of the data is a huge challenge for a model. And it's a challenge it's less of a challenge for the massive seeds, but it's a challenge for the massive seed models as well. It's a huge challenge for the light seed models, no matter what you assume in terms of how things scale for. And I think that's very interesting, and this is a new result. I should point out, we just published it, I guess, last year.
Thank Priya again.
Thank you very much.
And the next speaker is Silvia Bonoli, who will speak about forming massive black hole seeds in gas-rich galaxy mergers.